So formulas that you've been working with in my class. So like if you wrote a formula, so let's say we had like 5, 8, 11, 14, right? And so an explicit formula for that would be a sub n equals 5 plus n minus 1 times 3. Can I assume that that's kind of old news for you guys at this point? And again, what's nice about an explicit formula is that if I said to somebody, okay, based on that, find me the 143rd term, then you could just plug 143 right in. Formulas are so useful oftentimes in that sense that I just plug it in and I math it and it'll poof, magically just give me the 143rd term. It's pretty cool stuff. So today's is a little bit less cool than that. So today, I hesitated. Honestly, I thought maybe will this be the year I don't even bring this up? But the other type of formula that we need to talk about is not explicit, but rather recursive. And I care about what I do. I care about not giving you guys bad information. So, I spend time Googling things and looking things up that I want to know more about, like as a teacher, like why am I doing this? And the consensus really seems to be that recursive formulas, they don't really accomplish much. But I would be remiss if I didn't teach it to you, because then maybe you see it someday and you go, oh, I feel ripped off. Like we did the explicit ones, but I don't know how to do recursive. So here's what a recursive formula looks like. And I want to try to match the notation, but I'll be okay like this. So, and this is going to take a minute or five for a few of you to get your head around this. And honestly, what's nice about explicit is once the explicit formula clicked for you, you had to see its usefulness. But with this one, when it clicks, you're still not going to really feel much usefulness. And that's not just a you thing, it's a normal thing. So this a recursive formula contains two parts. I'm going to say that again. It contains two parts. By definition, a recursive formula consists of two things. Number one, a mention of what the first term is, and number two, the formulaic part. Can you translate to me, and by the way, kudos if you can you translate? I mean, you don't need any translation. The top one's the first term is 10, easy. What is that bottom nonsense even trying to say? You've got a really good math sense if you can decode this on your own.
It makes a common difference.
It is a common difference, I agree. Based on the recursive formula, could you right now tell me what the 34th term is? The answer is no. And I'll tell you this because you guys are all listening and you're listening with such great attentiveness. A recursive formula is only useful if you know the term before the one you're looking for. What this recursive formula says is that every term is 8 less than its predecessor. So if I wanted to find the 34th term with an explicit formula, I could just dive right in and do it. But with a recursive, I'd need to know the 33rd term. What would I need to find the 33rd term?
The 32nd.
The 32nd term. So you see the rub. You see where this is limited in its really practical usefulness is because what this is saying is, and this is the notation that usually bogs people down, but you guys are bright. It says that any term, the nth term, can be found by taking the n minus 1th term, meaning the term before the nth term, right? So like if I'm talking about the 85th term, then 85 minus 1 means I have to
80.
refer or reference the 84th term, which I don't know, correct? So a recursive formula isn't so much a matter of, hey, get in there and go find such and such for me. It's more just a statement of like pattern recognition. A recursive formula is more a way of saying, I see that the sequence starts here and I see that it behaves like this. But I am still going to ask you, and we're going to just put our brains together to problem solve this, but I am still going to ask you to find like a term further along the way using a recursive formula. And it's going to come back to the same logic that the explicit formula uses. And it really boils down to basic math. Tell me where to start, tell me how many jumps to make, and tell me the value of each jump, right? And if I can tell you all of those things, then you can get there. And so let's take a look at like this recursive formula, for example. Let's say that we were going to write out, so I'm just going to use this one since it's already on the board. If we were going to write out the first four terms of this arithmetic sequence, what would they be? What would the first term's 10, next term,
2,
next term,
-6.
next term, dot, dot, dot. So again, I can't just explicitly dive right in and find, bless you. I can't. So if I said, let's find a sub 81, I can't just plug 81 in somewhere, can I? But what winds up happening is I really, in the end, whether you want to, try to, or even know that you are, you're really going to wind up using explicit formula thinking. Because explicit's all about where do I start? How many jumps? What's the value of each jump? And that's just where our brains are going to go. So even if I don't tell Sutter or ask Sutter to write the explicit formula, his brain's still going to go there. So if I say, find me the 81st term, Sutter's brain's going to go like this. He's going to say, okay, roger that. I'm starting at 10 and I need to move how many times to get to the 81st term? 80 moves, and each move has a value of what? And that's, you see, it's interesting that even if we don't write an explicit formula, our brain still goes there, right? You do enough of this and you just start to see that that's the way it has to be, right? So can I still find the 81st term? Of course I can. Even if I don't write the explicit, of course I can. Today's assignment is going to be about, and there's another little thing I want to talk about, but the new assignment is just a bunch of this. Step one, determine if the sequence is arithmetic. Step two, write the recursive formula, not explicit. And then step three, find some random 54th term or 38th term or something like that. So anyways, this would be negative, what, 640. So that's negative 630 would be the 81st term. Got it? So the moral of the story is we write explicit formulas sometimes, but even if we don't, we can still think explicit formula E to help us predict future terms. All right, let's try this again, just because I know that not everyone's like 100% like locked and loaded. Someone write me an arithmetic sequence. Just give me the first four terms. I'll take any arithmetic sequence you got. Ready, go.
56,
56.
42,
Sorry, what was that?
-42,
Negative 42,
-140,
negative 140,
-238.
negative 238. And you're reading this off of somewhere, so we can verify that this is indeed arithmetic, correct? So it looks to me like Andy's written us an explicit, an arithmetic sequence that has a first term of what?
56.
56. So we write, this is part now, this what I'm writing here in these brackets is going to be the recursive formula. Okay. And remember, the recursive formula consists of two parts. Part one is a statement of what is the first term. The first term is obviously 56. And then step two is writing your a sub n term. And remember, this recursive is weird. We're not describing how to get somewhere. We're describing just how does each term become the next term, right? So in simple English, what would I say is the nth term? A sub n equals what?
-238. No.
I need to find a way to say that is what I always need, is the term that came before the nth term is called the n minus 1th term. What comes before the n minus 1th term? The n minus 2th term. What comes before the n minus 2th? The n minus 3rd, right? And so on and so on. You say n minus 3th? I will, well, why not, right? So don't get, again, hung up on the lingo or the notation here. We're just simply saying that any term can be found by taking the term that came right before him and subtracting how much? 98. And that is what a good recursive formula looks like. Tell me what the first term is and tell me how each term becomes the next. Again, does it allow me to go right in and find the 112th term? No, but it is what it is. Did that click okay? So that's how you do recursive. And so again, explicit is completely different, but our thinking winds up always coming back to the explicit thinking. Tell me where to start. Tell me how many jumps to make. Tell me how much each jump is worth. and I can get there, right? So I'm going to pause this real quick, but then I'm going to hand out the assignment 42 addendum. Actually, let's not do that. Let's get out that assignment from yesterday, the assignment 42. Um, and listen, God, again, what a joy it was to hear. I don't do that a lot as a teacher, where I just give you something and say, good luck, suckers. But I enjoyed watching you guys put your heads together and figure out how to find missing terms. And you were checking like all the boxes. It was really cool. So on assignment number 42, the first problem that you had was -13 blank blank -7. And again, there's some, dot, dot, dot here, dot, dot, dot here. But the point is, I'm focused on that little window. This isn't maybe the best example of this, but did you guys come up with a formulaic way to figure out D?
Yeah.
I want it to be reliable, repeatable. What is it?
What is it? Difference divided by the number of jumps.
Difference divided by the number of jumps. I
Plus
could not
one.
have said it better
Yeah.
myself.
But if it's number of jumps, you don't
It's number of
multiply it.
blanks plus one, but
Yeah,
it
but
is number of jumps. And so what we think about,
Um,
and the reasoning on this is a little bit simpler just because it's arithmetic. And arithmetic is plus, 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 or minus, minus, minus. So this is an easier cell. But the question is, how much am I adding each time? To figure that out, you take the term deeper into the sequence and subtract from it the term earlier in the sequence. That's what Zach referred to as the difference, right? Difference is always subtraction, but in this case, it changes to addition. What is -7 minus -13? Plus 13 makes it 6. And then what that means is there's a span of 6. To go from -13 to 7 is a span of 6. And now we just have to figure out, like, we got to divvy it up between how many dudes. And the dudes are the jumps. And so if you want to count blanks, feel free. Just make sure you add one. Otherwise, count the jumps. Either one will give you the same answer. So I count one jump, two jumps, three jumps. So you simply take the span of 6, you divide it by the three jumps. That's 2. And you can now say that the difference is 2. And then you simply go through and add 2. So -13 plus 2, -11, -9, so on and so forth. And what's nice about this is, like, in a while, I'm going to give you the challenge problems, and you're going to see that it works just the same. It's no matter how complex. And mind you, these challenge ones I'm going to give you, they're a lot harder. They're like a lot more intensive and taxing mathematically, but the same exact algorithm will work every time. Take the deeper one minus the earlier one, and then divide by the number of jumps it took to get from one to the other every time. Works like a charm. Got that? Okay, on the bottom half, we're doing geometric. And Zach, again, and some others of you, I think, cracked the code. So for an example of a geometric, we take this, I'll just use the first one. So we have -2 blank blank -128. We know that whatever R comes out to be, that it has to be positive. And the reasoning behind that is that if R were negative, then the signs would stagger. It would go negative, positive, negative, positive. And since that last term is disagreeing with that, then we know that R just has to consistently be some positive number. What would you give me as a description, any one of you, as a reliable way to find R?
I would say the right term divided by the left term.
I agree. Let's start with that. So we're always wanting to know, because remember that multiplication and division are just repeated addition and subtraction, and exponentiation is just repeated multiplication, right? Crazy. So I'm going to take the term further to the right, the -128, and I'm going to divide it by the early term, -2, and I'm going to figure out that there is 64. And I don't know how to say that. Like, there's some repetitive sort of multiplicative process resulted in 64 total uh, change. And this is where it's a little bit different, right? Any of you other guys, I won't let Zach steal all the thunder, but did you guys also come up with an algorithm for this? Brenda, what'd you figure out?
I could use the same equation. You have all of the factors except R, and you just find R.
That was the Sutter approach too, which kudos on that approach. I loved it. And so you guys just plugged the numbers in. So like on this one, you plugged it into the R times excuse me, A1 times whatever, right? And then, so I don't disagree with that. This, I think, is just a little bit, maybe a little bit quicker. Zach found a really cool way to do this, by the way. Super quick.
You take the in root of that number, and in is the number of jumps.
Again, it's always gonna come down to the number of jumps. So to go from -2 to -128 requires 1, 2, 3 jumps, which means you take the total 64 and you take a root of the third flavor and you're done. And R is 4, just like that. Okay. So there's 2 steps to the process. Step 1 is division. Step 2 is using a root. And the index or type of the root is going to be determined by the number of jumps we had to make. And so just like that, boom, R pops out. And we can now say that R is 4, which means that we take this times 4, -8, take this times 4, -32, so on and so forth. Let's practice this again. Yes, Andrew?
How do you do the roots on the calculator?
If you guys want to do roots on your calculators, hit the math menu and then go down. I think it's like option 5.
Yeah.
And then you will probably have already had to type in the index before that, I'm thinking. With most calculators, like if I want a cube root or a fifth root, whatever, I have to type in the index and then go math 5.
Yeah.
Okay.
You can offer this.
So another example of this would be like, I don't know, 2 blank, 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 blank. This is number 16, by the way. I'm sure you would have figured that out. So let's real quick. What's step 1? Divide deep term by early term. 8192 divided by 2 is 4096, I believe. And now all we're going to do is take 4096 and we're going to put it in some kind of a root. And the question is, what kind of root is it? And again, you can count blanks and add 1. Counting blanks and adding 1 is quicker than all the little arrows I keep drawing. So you just go 1, 2, 3, 4, 5, add 1 is 6. We're going to take a 6th root. So on your calculators, you're going to hit 6 and then go in, hit the math button, go down to option 5, and your calculator, these nicer calculators will probably actually put the 6 up there. The older models, like the TI-30s, they will say 6, and then there'll be a little X here like this. So these newer ones they're pretty high tech though. Do yours drop put the 6 up in the corner?
Okay.
Yeah, that's pretty high tech right there. Oh, that's right. And then yours gives you a little box.
You can do it either way.
Dope. Good. So anyways, 6th root of 4096 is what? 4, which means that the R value is 4, which means I can now just go times 4, times 4, times 4. Oh God, now what is that?
512.
512.
And then 2048.
And 2048. So I think that's a really slick, elegant way to do these problems. So remember, with arithmetic, you find the difference and then divide. With geometric, you find the ratio or quotient and then root. Super quick and easy. Having said that, I'm going to give you a couple things. I'm going to give you the challenge questions. I typed them up and made them look nice for you. Enjoy those, by the way. And then I'm going to give you the assignment 43, which is on recursive formulas. Can you handle all that? Rad.
Maybe.
I'll take maybe.
And get them all on the same term.
Not fill your.
Oh, I'm so sorry. Yeah, let me repause this one. A request was made that we go over this problem. So this is number 3 on that challenge sheet that I gave you. So the first thing you want to do is take the deep term and you want to divide it by the early term. Something you can take with you, you seniors especially that are leaving.
Yeah.
So when you take the deep term divided by this early term, hey, you two, hang on a minute, okay? When you divide by 2, you want to multiply the bottom by 2. So you don't need your calculator for that, okay? So if you take this thing at the back and you divide it by 2, then you just really want to multiply the bottom by 2. I don't know why that popped up here. Can I just make it?
I don't think it likes you.
Okay. Oh, this is really nice. So I'll just scroll this down and I did something. I clicked something. Anyhow, whenever in math class or life you want to take a fraction and divide it by two, make the bottom twice as big.
Okay.
So the number that we're going to be, and that makes sense to you, right? So we're going to be working with 15,625 over twice as much, 64. And then we are going to root it. And then the type of root is just going to be, again, the number of blanks plus one or the number of jumps. Either way, what is it? It is it is six. So we're taking a sixth root of the quotient. And I do believe that the sixth root of 15,625 is 5,
Uh,
I
25,
think.
250.
If we, yes, we take like, so 5 to the third is 125. So 5 to the fourth is 625. And then 5 to the fifth is that times 5, which is 3,125. So yeah, that checks out. And then the sixth root of 64 is 2. And so the answer is 5/2. I mean, that's not the answer. That's the R value, right?
That you multiply by.
So Anderson, you had asked, do you have any questions about that? Now would be a great time to ask. It's okay.
Oh,
5/2 is the R value. Yeah. So, and we got that by doing the sixth root of the top and also the sixth root of the bottom. You okay? So now we're going to do the annoying task of multiplying every term in line by 5/2. So, and this is just a basic skills nightmare. Some people are better at this than others, but the less we can use our calculators, the better. I mean, technology is great, but we don't want it to make us unable to do basic things, right? So like just envision with me 2 times 5/2. What do you see happening? It would just be 5 because the 2's cancel out, right? And then we do it again. And now we take that term 5 and we multiply it by 5/2. What do we get?
10.
25.
Don't the fives cancel out?
No one cancels out. It's 5/1 times 5/2, which is
25.
25/2. Good. And then we rinse and repeat. And now we're going to take 25/2 and we're going to multiply it again by R, 5/2. Does anything cancel?
That seems. Yeah.
No. So now we're going to get 125/4. And then we're going to go again. So the things canceling ship has sailed because all of our numbers on the bottom are going to be even and all of our numbers on the top are going to be odd. It's quite an uncooperative group of numbers. So we have 125/4 again times 5/2, which is
625.
625/8. And then repeat that process again. You see how we just keep taking every answer and just keep smacking it with R over and over again. So we're going to take 625/8 and multiply it by 5/2 again. And what do we get? It's not all that huge. It's 3,125. And then take the bottom times 2, which is 16. And then what feels good about these is just to kind of validate, give it like a little seal of approval, is to do it again and just verify that, in fact, if you take term number 6 and multiply it by 5/2, do you get term number 7? And when the answer is yes, then you can kind of do a little fist pump and say, boom, right? So use the algorithm to find R or D or whatever, whichever kind you're doing, and then just repeat application of that R or D over and over again. I know the one that I found to be the most fun was number 2, because there's a lot of fun fraction play in there, which if you're just a kind of person who puts everything in a calculator and lets it do all the work for you, then you won't really get much out of that. But I enjoyed the manual sort of side of the side of playing with the denominators and stuff. So because I like that stuff. Are there any others that you'd care to go over before I stop my recording?
Something fun with reading.
Wait.
Once I used decimals for most of them.
Okay.
Because